Okay, so today we're going to look at the factor theorem and explore a few different types of questions that come up with the factor theorem. Okay, so the factor theorem is very similar to the remainder theorem in the fact that I am going to go ahead and take the zero of each of my factors and just plug it into the polynomial. So in this case, my zero of x minus 1 would be 1. I'm going to take that 1, plug it into my polynomial, type that in my calculator. So if I end up with a remainder of 0, it means that the x minus 1 is a factor. So in other words, if I were to graph this equation on my graphing calculator, I should notice that 1, okay, is going to be a 0 of that particular polynomial. So we're just going to go ahead and check each one of these. So the 0 of x minus 2 is 2. We'll go ahead, substitute it into my polynomial using the factor theorem. Type it in my calculator. I end up with 0. And you can do that with the other ones as well. So x minus 2 is also a factor. X plus 2, if I take the 0, negative 2, and plug it in, I actually end up with a remainder of 36. So I know x plus 2 is not a factor. If I take negative 5, and plug that into my polynomial, I also get a remainder of 0. Okay. So then I know x plus 5 is also a factor. So the factor theorem helps me find factors of my polynomial. All right, so now we're actually going to factor. We know in Math 30-1 how important our notation is. So we're going to be really careful about notation. So you could take all the factors of 6, like plus or minus 1, 2, 3, and 6, and you could try all of those using the factor theorem to see which gives you remainders of 0. But that'll take really long. So your best bet, your quickest way to do this question, just graph it. Okay, graph the equation, and you will find that 2 and 3 both end up being zeros on your graph. So that means x minus 2 and x minus 3 have to be factors. So we know that by graphing, but we can actually prove that or show that using our factor theorem. So I'm going to write factor theorem here. And this is just me showing my work if I was asked to show this algebraically somehow. And then I'm going to substitute in 2 into my polynomial. And when I substitute that in, I end up with a remainder of 0. Okay, and then if I substitute 3 in, so I know p at 2 equals 0. I know p at 3 also equals 0. All right, so I know for sure x minus 2 and x minus 3 are factors, and I've shown that. So now to divide the rest of this polynomial, I'm going to use synthetic division. So it doesn't matter which one I use first. I'm going to choose 2. Okay. Go ahead and write the coefficients and constants. Carry that 2 down. 2 times 2 is 4. Negative 9 plus 4 is negative 5. 2 times negative 5 is negative 10. 7 plus negative 10 gives me negative 3. 2 times negative 3 is negative 6. Because I know this is a factor, I should get a remainder of 0. If I don't get a remainder of 0, it probably means I made a mistake somewhere. So now don't just leave this as your work. I have a lot of kids do this. So this is where those notation errors come in. So now I know that I have 2x squared minus 5x minus 3. So what I've done is I've taken this polynomial and I've divided x minus 2 out of it. So really, my polynomial now looks like this. This is my new polynomial. So I'm going to take whatever is left over here. So I have 2x squared minus 5x minus 3, my quotient. And now I'm going to go ahead and divide the x minus 3 out. So I'm going to take the 3, which is the 0 of x minus 3. There we go. Carry the 2 down. 3 times 2 is 6. Negative 5 plus 6 gives me positive 1. 3 times 1 is 3. Negative 3 plus 3 is 0. So I end up with a factor, or a quotient, of 2x plus 1. So now my final answer, all I'm going to do is I'm going to take those two factors I divided out. So I divided out x minus 2. I divided out x plus 3. And then I'm also going to include that last quotient. So again, to double check to make sure I did this right, if I were to graph this equation, okay, this polynomial here, it should give me the exact same graph as the polynomial here. This is just written in factored form. All right, so let's look at some diploma type questions. So the first question says, determine the roots of the equation and leave as an exact value. All right, so let's go ahead and graph this again and see if there's any factors that we know that'll work, just to save us time. And if we go ahead and graph, we know that 3 is a 0 of the graph, which means x minus 3 must be a factor. So I'm going to go ahead and use synthetic division. Three times 2 is 6. Negative 3 plus 6 is positive 3. 3 times 3 is 9. Negative 10 plus 9 is negative 1. 3 times negative 3, 1 is negative 3, with a remainder of 0. So I end up with 2x squared plus 3x minus 1 as my quotient. Okay, so I don't have any other zeros that I can divide out of this. Okay, I can look at this equation. Is there any way I can factor this? So 2 times negative 1 gives me negative 2. So are there two numbers that multiply to give me negative 2 and add to give me positive 3? No, there's not. So that means in order to determine these roots, I'm going to need to use the quadratic formula, which you do have on your formula sheet. So I have negative 3 plus or minus 3 squared minus 4ac all over 2a, which is 2. Okay, I'll go ahead and, I'm running out of room here. I will go ahead and type that radicand in my calculator, and I end up with an answer of negative 3 plus or minus root 17 over 4. That 17 obviously is hard to see. So this would be my roots as well as the original 3 that I took out. So my answers would be x equals 3 and then x equals negative 3 plus or minus root 17 over 4. I'm going to leave it like this because the question asks for the exact value. So that means I'm not going to type this in my calculator and get a decimal. Okay, so my next question here for the polynomial function, 2 of the zeros are negative 1 and negative 2. It can be determined that the largest zero, so we're trying to find the largest zero. All right, so I would use the factor theorem again, or I guess you could say the remainder theorem. If negative 1 is a zero of this equation, that means if I were to use my remainder theorem and substitute negative 1 in for all of my x's, okay, it should result in a polynomial that equals 0. So I have negative 2 plus 3 plus 10 minus 21 minus k equals 0. So I'll go ahead and I'll collect like terms. So I end up with negative 10 minus k equals 0. So then that means k equals negative 10. But remember, I'm not done yet. I'm not looking for negative 10, and that doesn't really look like a negative 10. Okay, I'm looking for the largest 0. So now what I'm going to do is I'm going to go ahead and graph this polynomial and replace the k value with negative 10. I'll just type it in my graphing calculator, and then I'll find the largest 0. So if I go ahead and do that, I should see that my largest 0 is 2.5, and that would be my final answer. Okay, so we're going to go ahead and skip this one. Really, if I wanted to figure out the remainder again, same thing. I would just use, okay, the 0 of my factor, which is negative 1 over 4, and I would go ahead and type this in the calculator. Okay, and if you do that, you end up with a remainder of 5. However, I do want to go through really quickly, just in case it shows up, how you would do this with synthetic division. Because when we've looked at synthetic division, we've always looked at terms that didn't have a coefficient. So this one does. It's going to change things up a little bit. So I start the same way. I use that 0. Okay, I carry down my 8. Negative 1 over 4 times 8 gives me negative 2. Negative 6 plus negative 2 gives me negative 8. Negative 1 over 4 times negative 8 gives me positive 2. 3 plus 2 gives me 5. So in my remainder 5, it just stays to the side, so that doesn't change. However, because I carried down this 8, and I didn't actually divide the 8 by my leading coefficient here, okay, of this factor, I actually do need to take my answer here, which is 8x minus 8, and I'm going to divide it by whatever that coefficient is. I'm going to divide it by 4 in this case. So I end up with 2x minus 2. Okay, so again, a great way to double check, if you were to take your quotient, which is 2x minus 2, and multiply it to your divisor plus your remainder, you should end up with this polynomial that you started with. Okay, so given that x plus 2 is a factor, determine the value of k. This is very similar to the question we already did, so I'll go through this really quickly. We take the 0 of x plus 2, which is negative 2. We just go ahead, plug it into our equation here. So we're replacing all of our x's with that negative 2. Okay, collect like terms, so we end up with 8 plus 2k equals 0. And then solve, k ends up giving me negative 4. All right, our last question for today is a little trickier. Same concept, but we end up having 2 unknown variables. So whenever you have 2 unknown variables and 2 equations, generally you're going to end up using systems, which you've covered in Math 10C as well as 20-1. So we're going to go ahead and set up our first equation with the information that we've been given. So using the remainder theorem, oops, I'm just going to go ahead and plug in that negative 2. So I'm going to take my m, replace my x with negative 2, plus n, negative 2, minus 4, and I'm just going to make this equation equal to my remainder, which is 4. I'll go ahead and collect like terms, and I end up with negative 8m minus 16 equals 2n when I rearrange everything. Okay, and of course I skipped a little bit of steps here, again, as a time saver. And now I'm going to go ahead, so that was my first equation, I'm going to go ahead and do the same with my second equation. So here my 0 would be 1 for my factor x minus 1. So I'm going to take that 1, plug it into this second equation here, which I guess is the same, and then make it equal to my remainder, which is negative 11. So I have m minus 2 plus n minus 4 equals negative 11. Again, I'll go ahead and collect like terms, and I end up with n equals -5 minus m. So you can see I are also rearranged because I'm going to use substitution as my method of choice here. So if I know n equals -5 minus m, I can go ahead and use this equation over here, substitute the n in, so that I'm solving an equation with just one variable. So from here, I'll collect like terms. I'll go ahead and add that 8m over. Oh, I'm running out of room here. So now I end up with a positive 6m. I'll add the 10 over, so I end up with -6 equals 6m. Okay, and now I know that m equals -1. To find the n, I'll just go backtrack and I'll substitute it in this equation here. So -5 minus -1 is going to give me -4. So there we go, solved it using systems. All right, so that is it for today. Go ahead and try some of these questions. Feel free to message me or let me know if you have any questions or need any help.